All right, grade 12 chemistry. This is our fourth lesson about intermolecular forces. This lesson is very important to help you understand the two labs that we're going to be doing in this unit, the surface tension lab and the boiling point lab, the second lab. Both of them rely heavily on intermolecular forces because the strength by which two molecules are attached or are attracted to each other determines both their surface tension and their boiling point. So here's what we're going to cover today. We're going to talk about electronegativity and bond polarity. We are going to then talk about dipole moments and polarity of an entire structure. Then once we've talked about the kind of things that affect structural polarity, we'll talk about what that means for intermolecular forces, including ionic forces, dipole forces, hydrogen bonding, which isn't really a bond, London dispersion force, and then we're going to rank them in terms of strength and talk a little bit about what this means for different chemicals. Intermolecular forces. Intermolecular forces are forces between molecules. So we're not talking about forces within a molecule, we're talking about forces between molecules. Kind of the easiest way to explain this would be, water. Water has this OH bond, and you could theoretically break it and make a hydrogen and a hydroxide, right? There would be a negative charge there and a positive charge there. You could break it. That is not the kind of force that we're talking about. This is an intramolecular force. This is a force that's that bond force. What we're talking about here is intermolecular forces, which is what happens when water is near another water molecule. And what happens there is that the oxygen with its lone pair of electrons kind of coordinates to the hydrogen, because the oxygen and the hydrogen, they really like each other. So the hydrogen is going to kind of try to get near the oxygen, and this hydrogen is going to try to get near a different oxygen, and so on and so forth. So it's that attraction. It's these little guys, which I should probably grab a different color for. It's these little guys here that we talk about when we talk about intermolecular forces. The molecules are separate, they're just attracted to each other. So they're not actually bonding, but it's like a magnet, right? When you have a magnet, you can pull them apart. Same idea. They're different magnets, but they're attracted to each other. This is the kind of forces that we're talking about when we talk about intermolecular forces. Major theme here is the difference between bond polarity and molecular polarity, so we're going to start with bond polarity. Bond polarity is based on electronegativity, and electronegativity is the pull for an outside electron. So this is why we have these focus questions here, back to ionic and molecular compounds. We say often in chemistry that metals steal electrons from non-metals, and the question is why. And some teachers in grade 11 and grade 10, they'll say, oh well, the metal wants to give up its electron. It wants to have a stable octet, so it wants to give up its electron. But this isn't true. This is blatantly untrue. There is a positive charge in the center of that atom, and that positive charge is going to be pulling on the electrons, on the valence electrons. It has an attraction for electrons. They do have an attraction. It's just very weak. Meanwhile, nonmetals have a very strong attraction for electrons, including the electrons that are on that metal. So essentially, if we kind of diagram it out here, if we take something like sodium, which is a big atom with 11 protons, and it's got the electron out here, and chlorine, when chlorine comes along, it's a smaller atom with 17 protons. Essentially, the force that the sodium does, that those 11 positives have for that electron, isn't as strong as the force that the chlorine has. And the chlorine, the force that those 17 protons on the chlorine have for that electron are so strong that the electron will actually jump ship and end up on the chlorine. So that's why metals and nonmetals have this stealing relationship going on. But on the other hand, you've got nonmetals and nonmetals. When you have two nonmetals, we say that they share electrons. That's pretty close to the truth. But what really happens is quite a bit more complicated. Let's say we have two hydrogen ions, right? Two hydrogen ions, or two hydrogen atoms rather. They look like this. But we of course know that they actually have clouds, right? A cloud of electron probability around the hydrogen. And this one has a cloud of electron probability around its hydrogen, around its core. And you know what? I'll change the color on that. The hydrogen. And the hydrogen. What'll happen is this hydrogen will exert a pull on these electrons. These electrons will get pulled towards that hydrogen, and this hydrogen will exert a pull for this electron, right? The clouds will get pulled towards each other, and what you end up with then is something that looks like this. The clouds turn into a bigger cloud of electron density, of what we call electron density. And both electrons are now contained within this kind of shape that's around both molecules. So when we talk about the quantum model of the atom, this is how the quantum model explains covalent bonding. The two the s orbitals, the 1s and the 1s, will come together to make this new thing that we call a sigma orbital. There's a sigma orbital, sigma 1 orbital, and there's two electrons in it, like that. And it's actually a lower energy state than these, right? These hydrogens, if we do the electron configuration of them, this is a 1s, and this is a 1s, like that. And when they exert their pull on each other, they come down into this thing, which is called a sigma bond. That's a little bit more complicated than what I wanted to get into, but that's the concept of sharing electrons. And note that it's because of pulls from both atoms, pulls from both nuclei. So that's what's going on there. So the difference between ionic and molecular is just the relative attraction of each atom to its electrons. When we have sodium and chlorine, the chlorine is so strong it can pull the electron away from the sodium. When we have two chlorines, though, they're the same strength, so they end up in that kind of tug of war, sigma bond type orientation, where the electron cloud is just now around both nuclei at the same time. Here's an electronegativity table. It's the pull for outside electrons. The behind my face there is just electrons. So it's the pull for outside electrons, and here we have the table. You can see that there's a general trend from bottom left to top right. Fluorine is the most electronegative element. Francium is the least electronegative element. Well, some people say cesium is the least electronegative element. Kind of depends on who you ask. Metals clearly have a low electronegativity, so a low pull for their electrons. Fluorine and the nonmetals generally have quite a high pull for electrons. I'd like to kind of focus in on oxygen and nitrogen here. They're very common as in organic substances. They're very common to find them in organic substances, and they have quite high electronegativities. So we'll keep an eye on those later when we talk about hydrogen bonding. So that's electronegativities. And the difference between these electronegativities tells you a lot about the bond character of a bond formed between two atoms. And really thinking of it as a tug of war is very, very, very helpful. So moving to that, here's electronegativity and what we call polarity. Polarity is a measure of how imbalanced the pull on an electron is. So if you're completely balanced, you might have that when you have two of the same element. So my hydrogen example from before would be what we call a non-polar, because it's not polar, covalent bond. It's a very equal sharing of electrons. So that's what we see here. But it doesn't have to be, two hydrogens or anything like that. It could be two of any element. You could have two chlorines, Cl and Cl. They both have the same strength, so the tug of war is equal. There's no polarity there. But what happens if you have hydrogen and chlorine? Right, you have a hydrogen and a chlorine. A hydrogen and a chlorine. Well, when we look back at our electronegativity table, we can get the idea of the strength between them. Hydrogen is a 2.1, so we'll write 2.1 for our hydrogen, 2.1. So that's like its power level, right? It's how strong it is. And chlorine is a 3.0. Chlorine here is a 3.0. So in this tug of war, chlorine has a stronger attraction for electrons than the hydrogen does. And what that means is that the electrons are going to feel a pull more towards the chlorine than they do towards the hydrogen. They do still feel a pull towards the hydrogen, but it's not as strong. And hence we get this kind of lopsided bubble, lopsided electron bubble towards the chlorine, and we call that a dipole. It's two poles, a positive pole and a negative pole. It's a polar covalent bond. Now, when the difference in electronegativities is very high, in the case of, say, sodium and chlorine, sodium, if we look back here, is 0.9, 0.9, 0.9, and the chlorine is 3.0. You have a bigger difference, right? The difference here is very high. I'm going to change this to green because it's bothering me. Green. Different green. There. The difference here is high. It's 2.1. So that means that the chlorine has this big pull for the electron, but the sodium has this really tiny pull. Tiny, 0.9. Very, very small pull. And it's got such a weak pull that the chlorine can steal that electron completely, and that's where we get an ionic bond. The difference in electronegativities tells you how polar the bond is going to be. This one here, there's a difference of 0.9. So that's quite strongly polar, right? 0.9. This one here has a difference of 2.1. So it's very, very strong. Now, that doesn't mean that this is twice as strong as this. Remember that electronegativities are relative, which is our keep in mind, and also these rules are kind of generally guidelines, but here are some guidelines that can help you understand the relative strengths of these bonds. Here's the general rule that a lot of chemists agree on. Ionic bonds are typically a difference in electronegativity of more than 1.7. So our sodium chloride certainly fits that with a difference of 2.1, because that's 3.0 minus 0.9. The difference in electronegativity is 2.1. Polar covalent is usually treated as 0.4 to 1.7 as a difference. That's why we say that this is polar, 0.9. And nonpolar is typically anything less than 0.4. So a good example of that would be carbon and hydrogen. Carbon and hydrogen have a very close electronegativity. Carbon 2.5, hydrogen 2.1. So the difference is right on that 0.4 cusp. It's a tiny, tiny bit polar, enough to kind of cause some headaches in certain organic chemistry contexts, but most of the time it doesn't really contribute to polarity. So yeah, nonpolar less than 0.4. So that's bond polarity. That is the polarity of any individual bond. The next section, which we're going to talk about, is how that affects structure polarity. So I'm going to pause and get some stuff set up, and I'll be back in 2 seconds. Okay, so we're going to talk about dipole moments and structural polarity. The important thing about that is this concept of dipole moment. A dipole moment exists for any bond. Every bond has its dipole moment. And if I bring it over here, right, there's a delta positive on the less electronegative one and a delta negative on the more electronegative one. That's HCl. It's the one that I diagrammed here, H and Cl. The difference is 0.9, so you know that it's polar covalent. So this dipole moment is a vector. It has a magnitude and a direction. So we can actually assign strengths to it and add them together and stuff like that. This symbol is the lowercase delta. If you know your uppercase delta in physics and in math, it means change. Lowercase delta means little change. So it's not quite fully positive, but it is slightly positive. So this means slightly positive, this means slightly negative. And there are plenty of ways to determine dipole moment. This is one of them, right? The concept of forwards and reverse, and the dipole moment is going to be going this way. To draw it, we simply draw a kind of a plus with an arrow towards the more electronegative atom. So that's what a dipole moment looks like. And this is MoleView. It's this really great software or online thing where you can draw, all kinds of things. You can draw structures, do weird stuff like that. But I'm going to erase that one because I don't want it. But much more interestingly than that, you can actually see them in 3D. So what I've got is I've got some structures here that I've drawn. I've got HCl, I've got ClCl, I've got HH. Then these are carbons in this one. So I've got carbon with 4 chlorines around it, carbon with 4 hydrogens around it, a carbon with 2 chlorines and 2 hydrogens. And we can look at them in 3D. So let's look at them in 3D now. Here's HCl, here's ClCl, here is HH, here is carbon with 4 hydrogens, CH4, here's carbon with 4 chlorines, CCl4, and then CH2Cl2, so carbon with 2 chlorines, 2 hydrogens. If we look at it, I forget how to translate, but if we look at these guys, we can actually ask this program to do a dipole moment. We can actually ask it to give us a dipole moment. So I can do that here, bond dipoles. When I click it, we get those arrows. You see those arrows? That's the bond dipole from the hydrogen towards the chlorine. So there's a bond dipole there from the hydrogen towards the chlorine. The chlorine has no dipole. Chlorine has no dipole, and the hydrogen has no dipole because they're pulling with equal strengths, so it's not giving us any dipoles. This guy, right, the hydrogen, the CH4, also no dipoles because carbon and hydrogen are so close together in electronegativity that it's hard to get a dipole off of it. But this one here, look at those dipoles, look at those bond dipoles. They are much more towards the chlorines, right? So there's a lot of dipole towards each of the chlorines. There's 4 chlorines there, and each one has a dipole force. But the most interesting one here is the last one, which is there. You can see a big dipole towards the chlorine, a big dipole towards that chlorine, but not a big dipole towards the hydrogen. Now that might be hard to see with the arrows, so we came up with a different way to do it. We can take away the bond dipoles, we'll clean it up, and we will do the bubble, the electron bubble. So red means more electron density on that side of the molecule compared to this side. And you can see that here when we have hydrogen chloride, that there's a lot near the chlorine and less near the hydrogen. We have chlorine Cl2. It's pretty much just an even lump. We have H2. It's also an even lump, a smaller lump because there's fewer electrons. CH4, methane, is also just a lump. It just looks like a lump. See that lump for methane? CCl4, the chlorines have these strong bond dipoles, but, overall, it's pretty symmetrical. And then CH2Cl2, the hydrogens have very, very, very little electron density, and the chlorines have a very, very high electron density. It almost looks like 2 of these stuck next to each other, even though we know that there's a carbon in the middle. Right, if I zoom in on that guy, there's that carbon in the middle. There it is, carbon in the middle. I think you can actually do it with translucency. There you go. So there's the carbon in the middle. And you can see the different electron lumps of my net dipoles. So that's a net dipole. Net dipole is the total dipole of a molecule. If I go back to here, I'm going to pause for a second and just focus in purely on CH2Cl2 here. So give me a sec. Here's CH2Cl2. The whites are the hydrogens, the greens are the chlorines. If we go to our electron cloud, you see that the chlorines are really pulling most of the electrons. If we look at our bond dipoles, there's a big dipole towards the two chlorines and a small dipole towards the two hydrogens. But there's also this thing here that says overall dipole. If I click it, what'll happen is you'll get the sum of these vectors, the sum of these bond dipoles. You have two dipoles kind of pushing down and two dipoles kind of pushing in. When we do the overall dipole, look at that, there it is. It's generally towards the chlorines. And that should make sense if we look at our surface, right? This is where most of the electron density is together. There's less electron density back here. So there's a net dipole as well. So if there's a net dipole moment, if the whole molecule has a net dipole, then the molecule is polar. I'm going to give you an example of the opposite, where the bonds are polar, but the molecule isn't. So I'm going to pause and set up a different molecule. The different molecule I'm going to set up is I'm going to take those two hydrogens and I'm going to replace them with chlorines. We're going to go hit 2D to 3D. Now we've got 4 chlorines. If I hit the bond dipoles, I've got bond dipoles all over the place. Right? There's bond dipoles, bond dipoles all towards the chlorine. If I hit the surface, right, there's my bond dipoles sticking out towards the surface. But if I hit net dipole, overall dipole, nothing happens. There is no net dipole. That little yellow thing that we had before is actually just in the middle. There's no net dipole. The reason for that is that this is symmetrical. We've got a pull out, 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 and out. So there's no preferred area of electron density on the outside of this molecule. There's no preferred area of electron density on the outside of the molecule. And so we say that the molecule overall is non-polar, even though each individual bond is polar. And that's what this is getting to. So H2O looks like this. Right, there's H2O. We've got a dipole towards the oxygen like this. Dipole towards the oxygen. So there's a net dipole towards the oxygen, right? There's going to be a net dipole towards the oxygen. We can prove this in mol view. So let's go over to mol view. We'll go to the 2D. We're going to take this away. We're going to make some water. Right, make some water. Go to 3D. There it is. We can look at its surface lucent. Right, there's the electron density. Here's the bond dipoles, both going towards the oxygen, and here's the overall dipole, very clearly towards the oxygen, just as predicted. Compare that though to CO2, right? CO2, which looks like this. CO2. We go back to this guy and we go back to 2D. Let's make some CO2. Delete carbon. And I want a double bond. There we go. There's CO2. Go to 3D. There's CO2. We can look at our electron cloud. And our electron cloud is just red. Right? There's no preferred place. From the outside, any other molecule will just see this kind of lumpy potato-looking thing when it looks at CO2. This is part of the reason that it's hard to make things react with CO2. When we look at the bond dipoles, right, clearly there's a dipole. There's a dipole towards the oxygen. Carbon is 2.5, oxygen is 3.5. The difference is 1. The difference in electronegativity is 1. But when we click overall dipole, there is no such thing. There is no overall dipole in this molecule because, again, the pull is equal in both directions, so they cancel each other out. It's like adding two opposite vectors, because that's exactly what it is. This is a vector issue. So not polar. Not polar. Even though the bonds are polar, this is not polar. Not polar. Not polar. Right? Bonds are. Bonds are polar, but the molecule isn't. That's for CO2. NH3. NH3 is interesting because it adopts this pyramidal structure. So N H H H. It's got this pyramidal structure. The reason that for the pyramidal structure is that the lone pair up here will push down on those bonds and push them downwards. So when we look at it in mole view, 2D, we'll get rid of that. We've got N H H H, 3D it. You'll see that pyramid structure. There's that pyramid. I can look at the bond dipoles. They all go towards the hydrogen, all towards the nitrogen, all up towards the nitrogen. I can look at the electron density, and it goes up towards the nitrogen as well. But if I go to the overall dipole, because everything's going towards the nitrogen, we have an overall dipole towards the nitrogen. So it goes towards the nitrogen. There's the overall dipole. And we've already talked about CH2Cl2, where we have a carbon with two chlorines. Well, can't draw chlorines. Yeah, two chlorines. Two chlorines and two hydrogens. And the bond dipoles work together to push stuff towards the chlorine. So your individual bond dipoles are towards the chlorine, and your net dipole is up, kind of between the chlorines. And we saw that in mole view earlier. So yeah, mole view is a really great tool for visualizing these things, and you can see the electron clouds really nicely. So if something wants to come along and bond to this nitrogen, if that thing is positively charged, it might really like to attach up here where there's a bunch of negative charge. If it's negatively charged, it might like to attach down here where there's a bunch of positive or a delta positive charge. So that's net dipoles and molecular structures and polarity. Shape is very important to polarity, so we're going to have a video about molecular shape coming out very soon as well. Yeah, so here CH4 nonpolar, CCl4, it has polar bonds, but the molecule overall is nonpolar. And CH3OH, everything's going towards the oxygen, so you got this net polarity towards the oxygen. So it's going to make this dipole over here. That is structure polarity. Next, we're going to talk about how that works with the different intermolecular forces, and we are going to pause, and I'm going to set some stuff up. Right. Intermolecular forces are forces between different molecules. Between different molecules. Please make yourself aware of that distinction. Right. This is the force that keeps two water molecules near each other so that they don't want to come apart. When we're boiling water, we are breaking this intermolecular force. Gas phase water is still just H2O. It's just separate from all its buddies. We haven't changed the formula of water when we turn it into gas phase water, into water vapor. Same like we don't change its formula when we turn it into ice. It's still just water, just solid water instead of liquid water. The difference comes down to intermolecular forces, and we have 4 classes of them. We're really 3 classes, but 4 classes of intermolecular forces that we want to talk about. The first one, the easiest to understand, is ionic forces. Ionic forces are the attractions between ions. So if I go over here and I take this away, this one is super simple to understand. When sodium loses its electron to chlorine, right? When sodium loses its electron to chlorine, I gotta put another one in there. loses its electron to chlorine. The sodium becomes positively charged, and the chlorine becomes negatively charged because it's got that extra electron that it stole from sodium. That extra electron that it stole from sodium, it becomes negatively charged. And pure electrostatic force pushes these two together. Pure electrostatic force pushes them together. They're not bonding in kind of the strictest sharing an electron sense of the word. They are just shoved together because there's electrostatic force. And if you had enough strength, you could pull them apart. And in fact, this is what happens when you dissolve salt in water. The water will actually come in and surround the sodium and surround the chlorine and pull them apart. I will link a really good video about that from the Museum of Nature down in the description, but essentially the water will coordinate to the sodium. When you put sodium in water, the negatives will go towards the positive ion. Negatives will go towards the positive ion, and the positives will go towards the negative ion. Right, the positive side of water, which is the hydrogens, will kind of coordinate to the chlorine, and that's what keeps them separate. That's what keeps these ions separate in water. So when we say you have salt in your water, what we actually mean is you have separate sodium and chlorine in water, kind of surrounded by water. But when there's not a lot of water around, the sodium and the chlorine are bound together very tightly. It makes a very strong bond, and it's very hard to break. This is part of the reason why it's solid at room temperature, part of the reason that it makes a crystal, and a few other things besides that. Salt has a melting point of like 800 degrees Celsius, so this is a very strong bond. When you have molten salt, these guys are free to move. They've actually got enough thermal energy to go apart from each other and be free to move. This is how they create sodium, actually. They melt salt, and then electrically they will put a negative charge in to draw the sodium out. It's very cool. Right, so that's ionic forces. Ionic forces are positives attracting negatives, very strong. Dipole-dipole forces happen when you have a dipole in your molecule. So this would be a molecular dipole. You see the same kind of positive-negative electron cloud that we saw in our mol view and this kind of thing, right? This has a dipole. Two ammonias next to each other would experience a dipole-dipole attraction to each other. Right, the negative part of one ammonia would like to be near the positive part of the other ammonia, so they will kind of coordinate themselves like this, right, like that, and that's what makes them hard to pull apart. Yeah. More polarity usually means a higher dipole moment, usually means a higher melting point and a higher boiling point. Not always. There's other things that can get in the way. So that's the first two intermolecular forces, ionic and dipole-dipole. These are the strongest forces, and ionic is like on another level above dipole-dipole. Like, again, 800 degrees Celsius boiling point for salt, or melting point for salt, compared to something like, I don't know, water or alcohol, which boil at around 100 degrees Celsius. Speaking of water, let's talk about hydrogen bonds. Hydrogen bonds aren't actually bonds. The reason they're called hydrogen bonds is that they are a very strong interaction, so strong that they're kind of like halfway between an intermolecular force and a pure bond. And they obviously involve hydrogen, and specifically they involve a hydrogen that is bonded to a very electronegative atom, usually just nitrogen or oxygen, although the definition has been revised in recent years to also include stuff like chlorine and fluorine. And if you ask IUPAC, the official definition of a hydrogen bond is hydrogen bonded to literally anything more electronegative than itself, but I'm not really going to buy into that. In our class, we're going to say just nitrogen and oxygen is going to be what's going to create hydrogen bonds. So you need a hydrogen bonded specifically to a nitrogen or an oxygen, and not only that, the nitrogen or oxygen, whatever it's, not only does it have to be bonded to a nitrogen or oxygen, whatever it's coordinating to has to have a lone pair on it. So this hydrogen is very strongly delta positive, and lone pairs are very strong concentrations of electrons, concentrations of negative charge. So the hydrogen, in a dipole sense, right, this is a dipole interaction, but it's very, 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 very attracted to this lone pair. A lot of biological interactions happen because of hydrogen bonding. If you've taken grade 12 biology, we talk your ear off about hydrogen bonding. So you can have it with oxygen and hydrogen, you can have it with nitrogen and hydrogen, you can have it with all kinds of things. It's very important in biology because this is kind of like the magnet of biology. It's a strong enough bond to stick together to make things hold in shape, like the folds of your proteins and the twist of your DNA and stuff like that. It's all created with hydrogen bonds, but it's weak enough that it's easy to open up and unzip and change shape. So DNA has to open up in order to get copied. Proteins have to fold and change shape in order to, like chomp stuff or move, like your muscle proteins or any of that kind of thing. So hydrogen bonds are really just very strong dipoles, and they're specifically, and you have to know this, they're specifically a hydrogen bonded directly to an oxygen that is coordinating to a lone pair on a different oxygen or nitrogen. So that is a hydrogen bond. It's a very strong dipole. If a molecule has hydrogen bonding capability, it's going to have a higher boiling point, a higher melting point than it should normally have, because these bonds are so strong, these dipole interactions are so strong. This is why water boils at 100 degrees Celsius, even though it's such a small molecule. Comparable molecules boil at much lower temperatures. Like even methane, CH4, is a gas at room temperature. It only goes liquid at like minus, 100, something like that. And then there's the last one. The last one is the London dispersion force. London dispersion force came about from studies about size and melting point. So methane, there's its boiling point, minus 164. So if it's warmer than minus 164, this thing will be a gas. Compare that to water, right? Water, 100 degrees Celsius boiling point, but it's a smaller molecule, or it's a comparable size molecule. But when you jump to butane, even though we haven't added any polarity at all, it increases the boiling point to 0 degrees Celsius. So butane is just barely a gas at room temperature. When we get to hexane, it's a liquid at room temperature. The boiling point is 68 degrees Celsius. You get to octane, the boiling point of octane is actually higher than water. Right? Water boils at 100, octane boils at 128, but there's no polarity here. There's no polarity to be found. There's no hydrogen bonds. You can't find a net dipole. There wouldn't be any net dipoles. This is just a boring lump of molecule. And maybe we can prove that by looking at mol view. Let's look at our last mol view for now. Delete that. Zoom out. We'll make a 10. And we'll go 3D with it. Here's decane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if we go to our surface lucent, or surface opaque, right? We don't even get one. There's no dipoles. Yeah, doesn't want to do it. It's so boring it won't even do a dipole for us. Clean, maybe high quality, maybe we'll go try it again. Nope. No dipole at all. Right, so back to this. And then if you get down to something like C17 to C50, everything past about 17, like wax, candle wax, this one has like 30 carbons, and it's a solid at room temperature, right? It's not even liquid, it's even stronger. But there's no polarity. There is no link to polarity. Bigger molecules just have a bigger melting point. And even more interestingly, longer molecules also have a bigger melting point. So if I bring my stuff over here, pentane is a liquid at room temperature, boiling point of 36 degrees. 2-methylbutane, which is also C5H12, has a boiling point of 27.9 degrees Celsius, just barely liquid at room temperature, but it is a liquid. But 2,2-dimethylpropane, which is still C5H12, is a gas at room temperature. The boiling point goes down. It's the same number of atoms, but the boiling point decreases. So something about being longer also means that it has a stronger intermolecular force. Remember, the boiling point is the amount of temperature it takes to rip this away from its buddies. A higher boiling point means that it would take more force. But they're the same mass, so clearly this one has stronger forces between it and other pentanes than this has to other 2,2-dimethylpropanes. So the reason for that is quite subtle, and it involves random electron distribution. Remember that these things have clouds of electrons around them. So the theory goes, when you have a long molecule, the cloud of electrons usually is pretty evenly distributed around the molecule. Usually. But random chance will sometimes have it, right, because they're always moving. A random chance might have it so that on your molecule, some of the electrons are a little bit closer to one side than the other. So, you might have less on this side and more over here, right? So random chance that you have more on one side than the other. This makes this side delta negative and this side delta positive by random chance, completely random chance. And then the magic happens. The magic happens in that a separate molecule next to it now feels some electrostatic force, towards, actually not towards the negative, right? The electrons would feel a force away from the negative, right? They would run away. The electrons on this molecule would run away from that delta negative charge that's building up over here. But again, that charge was random chance. And eventually that will induce a different dipole and a different dipole. So this is called the induced dipole. This is called the induced dipole. Induced dipole. And you have a dipole developing where no dipole should happen. So this is the induced dipole. The random chance creates a temporary dipole. Using this, you can probably now understand why longer molecules compared to wider molecules, like why this longer pentane has a higher boiling point than this stubbier 2,2-dimethylpropane. It's because it has more of a chance to get this kind of distribution. The stubby dimethylpropane can't do that nearly as effectively. So those are London dispersion forces, and the kind of takeaway from them is that when you have more atoms, you get more attraction because there's more electrons to have that random motion from. And if it's longer, you also get more attraction. So let's do our final thing. Let's rank them. Ranking the forces. Ranking the forces is our last piece. And this is just the general thing, right? What does it mean together? Van der Waals was this Dutch guy. He put this all together to say, hey, boiling points are just the sum of total attraction or repulsion. So that's the total attraction or repulsion. A higher Van der Waals force means a higher boiling point, a higher melting point, and a higher surface tension. And it's because the molecules, the individual molecules, are sticking together more tightly. And a higher polarity often means more solubility in water, but size also matters a lot. Water needs to surround something in order to dissolve it. Big molecules, even if they have polar bonds, might not be soluble in water. This is part of the reason that water sticks to glass really well but doesn't stick to plastic very well. Glass has polar bonds, and plastic has non-polar bonds. So here's the summary. More intermolecular forces means a higher boiling point and a higher melting point. It's not like perfect, but it's pretty good. Ionic is the highest. This is in terms of strength, right? This is in terms of strength from low to high. Ionic is absolutely the strongest because the two things are right next to each other and they are positive and negative, full positive, full negative, right up next to each other. Very strong force. Dipole-dipole and H bonds by extension are based on molecular shape and those dipole moments, those electron clouds. These are weaker, but hydrogen bonds are a particularly strong instance of dipole-dipole forces. They kind of approach ionic strength in some cases. That has to have a hydrogen on an oxygen, a hydrogen directly on an oxygen or hydrogen directly on a nitrogen, that hydrogen has to be coordinated to a lone pair in order to be considered a hydrogen bond. And the last piece is the London dispersion force. Every molecule has a London dispersion force. Even something as small as helium has a London dispersion force. Every single molecule has those forces. And this thing called VSEPR helps us predict polarity and intermolecular forces. We're going to talk about VSEPR in the next video because this one got a little bit long. The last thing that I want to say is these trends in boiling point and melting point aren't absolute. And the classic case here is the boiling point versus the melting point of water versus hexane, or water versus octane. Water versus octane. Water, of course, boils at 100 degrees Celsius and melts at 0 degrees Celsius. Octane boils at 125 degrees Celsius, so you expect that it would maybe melt at a higher temperature than water, but that's not true. I have forgotten the melting point of octane. I did look it up before I started this, but I've forgotten it. I'm going to look it up for a sec. I love that pause feature. The melting point of octane is minus 57 degrees Celsius. Minus 57 degrees Celsius. So even though the boiling point is higher due to more kind of forces on it, the melting point is actually lower because there's kind of different transitions and different things become more important for melting point versus boiling point. Don't take it as a 100% true thing, but the general idea of hydrogen of this organization works pretty well. That ionic is the strongest, then hydrogen bonds, then dipole-dipole, and then dispersion. I want to ask you questions about this on a test. I'll make it super obvious. I'll have very similar molecules, except for this one will make hydrogen bonds, but this one won't. And then it'll be really clear which one has the higher melting point or boiling point. So I hope that helps you understand your lab about surface tension and the other lab about boiling points. We'll take this stuff up in class. Thanks, and I'll see you in class.